All right, let's end this chapter now looking at when will a reaction run via the SN1 mechanism, when will it run via the SN2 mechanism, and we'll work some examples. Basically, we're looking at four factors on which mechanism it's going to go. We'll look at the nature of the alkyl halide, the substrate, the nature of the substrate, which in this chapter is the alkyl halide. We'll look at the nature of the nucleophile. We'll look at the nature of the leaving group, and then we'll look at the nature of the solvent. And we must start out by saying the nature of the alkyl halide and the nature of the nucleophile are the most important things when determining if a reaction will go SN1 or SN2. Now, the nature of the leaving group, truthfully, we need to look at the leaving group. We kind of have to look at it first because that will tell us if a reaction is even going to happen. If the leaving group is a very poor leaving group, then it won't go SN1 or SN2. If it's a good leaving group, it can go SN1 and it can go, or it can go SN2. So usually we look at the leaving group first just to make sure the reaction's even going to go. And then assuming we've got a good leaving group, then the most important things are the alkyl halide and the nucleophile. If we can't get our answer from these two, then we will look at the solvent, but that's our least important factor by far. So our most important factor, so we have a good leaving group, is the nature of the alkyl halide. If it's methyl or if it's a primary alkyl halide, the reaction will go via the SN2 mechanism. If it's a tertiary alkyl halide, the reaction will go by the SN1 mechanism. If it's a secondary alkyl halide, then it could go by SN1, it could go by SN2. We don't know yet. So the first thing we look at is alkyl halide. Second thing we look at is the nature of the nucleophile. In our SN2 rate law, the nucleophile is in there. The nucleophile is not in the SN1 rate law. So the better the nucleophile is, the more negative it is, the better it's attracted to positive charge, the faster the reaction goes in an SN2 mechanism. So strong nucleophiles and high concentration favor the SN2 mechanism. That's going to be the faster reaction. Weak nucleophiles then don't care as much about the substrate because the weak nucleophiles are attacking an extremely positive carbocation, so weak nucleophiles prefer the SN1 mechanism. Because here's the deal, if our nucleophile is a weak nucleophile, we know the SN2 is a much slower reaction. Strong nucleophiles give us fast SN2 reactions, weak nucleophiles give us slow SN2 reactions, such that the SN2 reaction for a weak nucleophile is so slow that the SN1 mechanism is the faster one, so much more of the molecules go via the SN1 mechanism. For example, let's look at examples of this. Here we have our methyl cyclohexane with a bromine on the opposite side, and we're reacting it with OH. So the question is, does this go via SN1 or SN2, and what would the product or products be? Well, we can see that this is a secondary alkyl halide. Secondary alkyl halide, okay, both SN1 and SN2 are possible with secondary alkyl halides. But we note hydroxide is a strong nucleophile. So if we have a secondary alkyl halide and a strong nucleophile, secondary alkyl halides could do either mechanism, but strong nucleophiles are favored by SN2. We know this will be the SN2 mechanism. And since now we've figured out it's SN2, we also know that the OH has to come by backside attack. So the OH is going to come from the opposite side of the bromine. The OH is going to be going back in the product, and the hydrogen that is currently going back will get flipped out. So we'll end up with this guy right here, the OH back, the hydrogen out, because this is SN2, because it's a secondary alkyl halide and a strong nucleophile. What if we start with the same alkyl halide, our same secondary alkyl halide, but instead of the strong nucleophile hydroxide, we put the weak nucleophile water in there? Well, secondary alkyl halide, weak nucleophile, secondary can go either SN1 or SN2. Weak nucleophiles go via SN1. So we know this will be an SN1 where the bromine will leave first giving us a carbocation intermediate that is trigonal planar. So now we know, because it's SN1 and we have trigonal planar carbocation, that this water could come in from the top side or it can come in from the bottom side. So here we've got our water coming in from the top side. Here it is coming in from the bottom side. But we have to go one further. We know that this product, these two products, have an oxygen with a positive charge and a hydrogen on it. So we know that a deprotonation reaction is going to occur to give us OH and coming out at us from this product here, and OH going back from this product here. Note, that's quite a bit. The question was, this cyclobromomethyl-cyclohexane and water, what do we get? Think about all the different things you have to think about in order to get this question right. You have to know secondary, weak, you have to know it is SN1, therefore you need to know that this water can come in from the top and the bottom. And you have to know that you get a deprotonation under these situations to give us these two products. Note, this product here was the same we got with the SN2 reaction. So if all you wanted was to have the hydroxide trans to the methyl, you would have reacted with hydroxide and done the SN2 mechanism. But if you needed both of them, or if you needed the OH, the hydroxyl group, cis to the methyl, you'd have to run it under SN1 conditions with the weak nucleophile to get this 50-50 mixture here of the cis and the trans products here. Okay. As we talk about leaving group, yeah, good leaving groups increase the rate of SN1, SN2. So truthfully, the best thing is look at the leaving group first. The last thing is the solvent. It turns out polar protic solvents, alcohol, water, they are especially good for SN1. Polar aprotic solvents, DMSO, acetonitrile, acetone, they're good for the SN2 mechanism. That being the case, if you were running this reaction right here and you had this secondary alkyl halide and a strong base like water, this will go, or like hydroxide, this reaction will go SN2 no matter what. If you had water in there as the solvent, it wouldn't matter, because whenever you have a strong nucleophile and a weak nucleophile together, it is a strong nucleophile that will determine the mechanism. So we have a secondary alkyl halide, OH minus, this will go SN2 no matter what solvent. Even if you put it in a polar protic solvent, such as alcohol, ethanol, this reaction will still go via SN2 with strong base, because the solvent really doesn't play a role unless you're, truthfully, the solvent, the major role it plays is with our alkyl halides. Recall that in polar aprotic solvents, which we generally run SN2 reactions at, substitution reactions, that iodide's the best leaving group, fluoride is a decent nucleophile. Recall with a polar protic solvent, all of a sudden fluoride becomes an okay leaving group and iodide becomes a decent nucleophile. So most of the time, that's when we really have to worry about the solvent. All right, so that does it for the lecture part. Let's look at some example reactions here and see if we can figure out which way it's going to go. So the question is the same for all of these. Here's our reaction. What are the products? What mechanism will it go through? And what are the products of the reaction? All right. So where to begin? Well, let's begin at the top. We've got CH3, CH2, CH2I, little propyl iodide, or 1-iodo-propane, and we act it with OH minus. Well, what do we know about this? What can we say about this reaction? Well, tell me about, first of all, do we have a good leaving group? Yes, iodide's a good leaving group. Okay. Tell me about the substrate, primary, secondary, or tertiary. Well, this is a primary substrate, so already we're thinking SN2. Is this a strong or a weak nucleophile? This is a strong nucleophile. So, okay, primary substrate, strong nucleophile. This is an SN2 mechanism all the way, and we know Therefore, it is going to be SN2. And our product is going to be CH3, CH2, CH2OH plus I minus. And we've got that down, not a problem. Note, this carbon is not chiral, so we do not have to worry about stereoisomers or anything like that. Okay, let's look at the next one. What do we have here? First of all, we have a good leaving group. Yes, bromine's a good leaving group. Not a problem. So next question is primary, secondary, tertiary substrates. This is secondary. Secondary substrate, well, that can go either SN1 or SN2, so we haven't figured anything out quite yet. Cyanide, is this a weak or a strong nucleophile? Recall, cyanide is a strong nucleophile. Secondary substrate, cyanide strong nucleophile. Not a problem here. This is going to go via SN2, because if we have secondary, which could go either, and strong nucleophile means SN2. And we've got a cyanide right here. Note, in this instance, I did not indicate the stereochemistry about this carbon. This is a chiral carbon right here. Yes, that is a chiral carbon. It's got a propyl, ethyl, and a hydrogen and bromine on it. But since I did not indicate the stereochemistry here, we don't have to indicate the stereochemistry of our product. If I did indicate the stereochemistry, note this is SN2, so we would have gotten inversion of configuration. All right, next problem. Chloride's a good leaving group. Yay, we don't have to worry about that. Primary, secondary, or tertiary substrate here. Well, this is tert-butyl chloride. This is a tertiary substrate. So right now we're thinking SN1. Strong or weak nucleophile. Recall water is a weak nucleophile. All right, weak nucleophiles prefer SN1. We are SN1 all the way here. But what's the product going to be? Note, what would be acceptable to me is for you to just draw that. That is going to be the net product of the reaction. Note, when this first occurs, note the leaving group's going to leave first, then the water is going to attack, and we will end up with this beast, with this OHH on here like this. Note that that oxygen will be positively charged. And recall, anytime we have a positively charged oxygen with hydrogens on it as our product, a deprotonation reaction, extra water is going to come in, snag that hydrogen to give us our overall product. All right, so the answer to this is always going to be this. It will not be this. This is just another intermediate in this is in our overall reaction. This is the product of the nucleophilic substitution part, the SN1 substitution, but we know it won't stay there. We know we're going to get that deprotonation reaction, so always give that deprotonation reaction, whether it's SN1 or SN2. All right. Okay, what do we have here now? Well, I'm going to change this up just a tad. And let's say that the bromine is coming out at us and this methyl group is going back. Okay. Tertiary alkyl halide. Good leaving group. Weak nucleophile. This is going to go via SN1. But note, I've noted the stereochemistry here. So what are we going to get as our products? Okay, recall this is SN1. We've got an ethyl, a propyl, and a methyl coming off of here. We realize that we are going to first thing that'll happen is the bromine is just going to leave, giving us a carbocation that is trigonal planar, which means this group can come in from either side. Note once this guy attacks the carbocation, that we're going to be left with something that kind of looks like this. Stage 3, OH, CH2, CH3, and a positive charge. Recall bromine left as bromide ion, negative charge, which means our other product here, our organic product, has to have positive charge. And it's got a hydrogen, so we're going to get deprotonation there. And so our final product will not have this hydrogen on it because we'll get deprotonation. But also note that since the carbocation is trigonoplanar, we will get a 50-50 mixture of the OCH2, CH3 coming out, and this CH3 going back, plus the OCH2, CH3 going back, and the CH3 coming out. So yeah, this tertiary alkyl bromide here that is chiral, plus this weak nucleophile means SN1, which means trigonoplanar carbocation, which means we get a 50-50 mixture of the two enantiomers, and they're both going to be the deprotonated product. So this is the answer to this question right here. Okay, next one. Okay, do we have a good leaving group? Yes, all right. So primary, secondary, or tertiary. This is a secondary substrate because there's 2 carbons here. Secondary alkyl halide. Okay, SH. Oh, recall, this is a strong nucleophile. Okay, this one's not too bad. Secondary could be SN1 or SN2. Strong nucleophile means it's going to go SN2. We know that means backside attack, which means, note, the only inversion of configuration happens at the carbon that gets attacked. Even though this carbon here, we see its stereochemistry, the reaction is happening over here at this carbon. So we don't change anything at this carbon over here. We know our SH is going to come in from the back side. So it'll be our SH down. And this hydrogen here, as the SH comes in from the back side, this hydrogen is going to move up. So we get this product and this product only. Cool. What if we had the same starting material and had HOCH3 here? Okay. Good leaving group. Secondary alkyl halide. Weak nucleophile means SN1. Note up here, this was the SN2 mechanism. Secondary strong, SN2. Secondary weak, SN1. Ooh, note we've got this hydrogen on here, which means we're going to get a deprotonation reaction at the end. Hopefully at this point you can see, all right, secondary can do SN1 or SN2. Because it's weak means SN1. Because we see our stereochemistry means we're going to get a mixture of our 2 isomers, the cis and the trans, and we're going to deprotonate this at the end. So hopefully you say easy peasy. Nothing happens over here. The CH3 is always going to be coming out, and this hydrogen always going back because no reaction's happening over here. It's all happening at this carbon. And I am going to get coming out at me OCH3 and going back the hydrogen, the cis product. And I'm also going to get this here, CH3H, hydrogen coming out, OCH3 going back, the trans product. Ooh, another question. What's the relationship between these 2 products here? The cis and the trans? Note, these 2 are diastereomers. Cis and trans isomers are diastereomers. They are not enantiomers because they're not mirror images of each other. They're not non-superimposable mirror images of each other. Okay. One last one just for fun, what if I had this? What will happen if we run this reaction? Hopefully you can see our first question that you should be asking, how good is our leaving group? Hydroxide. Is hydroxide a good leaving group? No. No reaction. No good leaving group. All right, that does it for this chapter, substitution. Next chapter, we will go into elimination reaction.